Hello, everyone. Welcome to today's live stream. We're joined by Thomas Adler, and he'll be talking about nestedly recursive functions.
Exciting. Welcome, Thomas.
Thank you.
Cool. Do you want to tell us a little bit about what a nestedly recursive function is and then present to us?
Sure. Yeah. Maybe I can share my screen. I can.
Oh, absolutely. Go for it.
All right. Can you see it all right?
Mm-hmm.
That's good.
All right. Cool. So, yeah. So, hi, everyone. I'm Thomas. Maybe just like 2 sentences about me. I am originally from Switzerland. I studied economics in London. Then I switched into tech, into data science. And I was actually for 2 years working with graph databases and knowledge graphs. And that's how I got really more deep and interested in network science. And then now I'm going to be starting a PhD in computer science with a focus on all aspects of network science in China. And so this is a project I worked on the Wolfram Summer School the past month. And I think the first thing that we need to remind ourselves is the first word of the title is exploring. So this was really kind of an exploration. There was no very specific clear goal about what we were trying to find. The general idea was we wanted to analyze and explore what these nestedly recursive functions could do, what they could look like, and what are some interesting paths to go down into. So if we want to summarize maybe in a sentence what the project wanted to do is we wanted to find interesting patterns out of these nestedly recursive functions. And we found those interesting patterns in the call graphs of these functions. And we're going to define that as we go along. So first, we want to focus first on what a recursive function is. So the best example of a recursive function is the Fibonacci sequence, where if you want to calculate a specific number, you need to know what the results of the function with a different input was, usually a smaller input. For example, here, f of n equals f of n minus 1 plus f of n minus 2. This is a simple recursive function. It's essentially a function that calls itself. A nestedly recursive function was more or less coined by Stephen Wolfram, and it's not that complicated. It's just a function that calls itself multiple times. So the recursive functions are nested into each other. This is an example that was pretty famous from the Hofstadter Q sequence, where Q calls itself in a specific pattern.
Okay. Do you mind zooming in a couple notches there, maybe to control it? Yeah, perfect. Thank you.
Yeah, is that okay? Cool. So we've defined recursive functions. We defined nestedly recursive functions. Now we want to define what a call graph is. Very simply, a call graph tells us what values each function needs to compute to get its result. So if we look at f of 10, to calculate f of 10, we need to know f of 9 and f of 8 for the Fibonacci sequence. But to calculate f of 8, of course, we need to know f of 7 and f of 6. And essentially, we go on and on until we need to meet a certain base condition. And in the Fibonacci sequence, the base condition is f of O equals 0 and f of 1 equals 1. So you see the structure of the graph is actually already interesting because the red arrow means that it called, so f of 10 first called f of 8 before calling f of 9. And we see that essentially the red arrows are the first ones called, and it goes all the way down to the base condition because that's the final result we actually get. And then we go all the way back up. So the red arrows lead to f of 0, and then the red arrows lead to f of 1 as well.
Sorry, how do they go back up? If we start at f of 10, how do we know if it's going red or blue there at that point?
So in this case, it's more of essentially just how the function that we created, whether it treats first f of 9 or f of 8 first.
Oh, I see. Okay.
At this part. But first, it goes all the way down to reach the base condition, and then it can go all the way up because f of 2 now can be computed.
Oh, I see. Okay.
Yeah.
And I guess just like a little point of formatting. The f of 1 should be the f of 1 equals 1 should be a base condition that highlighted gray.
Yeah, I guess so. Yeah, this should be highlighted.
Got
So yeah, that's essentially what a call graph is. And this is like a simple call graph. And all the graphs that we're going to see in this presentation are going to be the call graphs of all types of nestedly recursive functions.
Mhm.
And so as I mentioned before, the idea is that we want to see there's some kind of complexity that emerges from these simple functional forms that we're passing. So here in the Fibonacci sequence, if you imagine that we use we put an n equals 1,000 or 100, and it would just always kind of look the same, like this kind of
Yeah, just be
simple
this
all the way down. Yeah,
this ladder going up. The
exactly.
Fibonacci.
A ladder, better better term. So it'd be just a whole ladder. So that's not that interesting. So in the past already, Stephen Wolfram already looked at a few interesting forms. And these are just like two examples which create like interesting patterns.
Ooh, cool.
So this is like a reference from one of the NKS book. It's also recorded in the Encyclopedia of Integer Sequences. This one looks like kind of a cone shaped, and the function is here. It's actually also relatively.
So it's f of n equals 1 plus f of n minus f of n minus 1. So
Exactly.
it recurs twice.
Yeah,
Okay.
exactly. This is what we call like nested. And then this is a second example, which also gets a nice shape of like an ammonite. And we essentially have, so f of n equals f of n minus f of n minus 1 plus f of n minus f of n minus 2 minus 1.
And the base conditions are like in the center?
The base conditions are here. So
I mean, like in the graph, they would be.
Yes, exactly. They're in the center. Yes. They all reach the center. And so the different colors is the order of the calls. So red is the first, blue is the second, and we've got green and kind of maroon, So green is the third, and then this kind of brownish color is the fourth.
Cool.
Are these functions named? Do they have names for this, or is this just
the names of this function?
Yeah, like this isn't a Fibonacci series or something. It's just NKS book.
Yeah, it was. Well, actually, we can actually maybe look if there's actually named or not.
Got a numbered name. Wow. Okay. Interesting.
So it doesn't seem to have a specific name, or I can't find. All right. So and then you see here we go up to the fourth level. So this I'm not sure what color this is, like dark green, let's say. Means that it's been like there's like 4 calls, and here we can see actually there are 4 calls. F of n, then this f of n, and here f of n, and another f of n. Okay, so that's kind of like introduction of what these functions are and these call graphs. Now this part is more of a, let's say, implementation exercise. But there was actually like a big part of the project, because that's if we made this implementation work, it enabled us to actually analyze all types of functional forms. So in most programming languages, including Mathematica, you can actually program a Fibonacci sequence very simply by a function calling itself. Here we have the initial conditions. Whenever this function is an input of 0, it gets 0, 1, and 1. So that's our base condition. Here we have an input of n, and we just add the function itself with the input n minus 1 and n minus 2, just as we saw before. So yeah, we can actually create this function very simply and create a Fibonacci sequence out of here.
Right, and then a point of order, I guess the function call gets more efficient if the lesser values are cached in memory or stored in memory, so that you don't recompute the same sub value multiple times. Otherwise, the complexity can get it can take more computation just to get further down the line.
Exactly, and that's actually what we're going to try to implement. And it's like this kind of like memoization, so they memorize the values as we go along. But actually, the first limit that we kind of found was this recursion depth limit. So actually, out of the box, if it calls itself, as someone is a recursion limit. But actually, we can change this recursion limit manually in the backend when we use Mathematica. But
Yeah.
I guess there's two reasons why we don't want to do that. Is one, we don't really want to tinker with the backend manually. And secondly, it's actually like an interesting exercise for us ourselves to implement it from scratch to see as well how we can optimize it further, as you say, with this memoization.
Mm-hmm.
And yeah, these were the three main parameters that we really wanted to make sure that were working. One is the memoization, as you mentioned, Dugan, is when we don't want to recompute every value every time we meet it. We want to cache it somewhere. We want to avoid this recursion depth limit, and we want to accept all kinds of functional forms. So however fancy your function looks like, we want to be able to deal with it. So there's like 1,000 like recursion or like nested functions or anything like that. We want to deal with it. So this is when we come with the first iteration of our recursive function, and it's we were mostly focusing on memoization. And this was actually already implemented, kind of already partly written by Stephen Wolfram and Brad Klee. And I'll show you the code. We don't need to go very deep into it, but there's just two things that are important. This is what it looks like. This whole part here essentially is important because it kind of pre-processes the function in a way that can be then dealt with this function subfun. So this is then just extracts, okay, what is the function? What are each part of the function that needs to be evaluated, and which parts are we actually missing from the evaluation? So if in a Fibonacci, it's going to look, okay, we need f of 9 and we need f of 8 to calculate f of 10. So they kind of separate those out, and we know now that we need to calculate these two functions. That's kind of the general idea. And it's pretty flexible, so we can pass all kinds of functional forms. And then the main thing that happens here is subfun. And we still call subfun, subfun calls itself still. It just calls itself with a memo, which is an association, and caches the values that have already been calculated before. So it really focuses on memoization. So this is this function, and it's mostly called again here in the body of the function. That's kind of the two main points. It accepts all kinds of functional forms and it memoizes values.
So this is sort of like a helper algorithm that starts at the beginning and keeps track of, like, first of all, it keeps track of the base conditions, right? And
Yes,
then
exactly.
builds the rest of the tree from the bottom up and goes up. Okay.
Yes.
And at each step, it records its value to the memo, and
exactly.
it looks for uses that to advance its knowledge
so it looks at the memo.
tree.
Yeah, it looks at the memo, sees if something has been calculated. If it hasn't, then it calculates it. If it has been calculated, it can just retrieve it. Yeah, it avoids like too much recomputation. All right, and then the second iteration, and that's the one I implemented during the summer school, is essentially because when a function call itself, it still does some kind of there's still some kind of process in the backend where it goes very deep up until the base condition, and it goes back all the way up to compute the missing values. But what we wanted to do, partly for like kind of the intellectual exercise, second to have more introspection into how the function works and how we're actually storing values and storing values. We want to implement this stack ourselves. So usually when a function calls itself in a programming language, it usually uses a stack anyways in the backend. But we're essentially implementing that straight in the code. Yes, that's the general idea. This is probably also a reason why it's very hard to optimize it to really be quicker than a function that calls itself, apart from the recursion depth limit, because there's lots of optimization done in the backend that we can't really do ourselves, or that wouldn't make that much sense to make. So I'll just show you. So this is this nested recursion function. Again, this is some pre-processing. And here again, this is what we call the stack fun. So this is the function that actually computes the value. And you see we're not passing any memo here. Why? Because essentially for the whole duration of the computation, we're staying in this function. So we only call this function once. And the general idea is that there's two stacks. One, there's like a function level stack where we look at each function and we see, okay, do we need to calculate other functions? And then there's, for each function, apart from having to call other functions, you have to compute other values. For example, 1 plus f of n minus 1. So first we need to calculate f of n minus 1, then we also need to add 1 to that. So that's kind of why we have two stacks. So in practice, actually, there's one stack, and then there's two while loops. One goes through the stack, and the second while just keeps track of have we computed all the elements of this function or not. That's a general idea. And we do that, which is very hard to read, but we essentially, for each function, have an association, and we have a tracker of at what, like, have we essentially finished evaluating all the parts of a specific function. So that's I'm not going to go too much more deep into this unless you guys have questions. That's the general idea. Okay.
Thanks.
So we did a little bit of like some comparisons.
Mm-hmm.
So actually, when we were just looking at simple Fibonacci stuff, as we saw, both are recursive and stack-based. So our two implementations don't have recursion limits. So that's one part done. We, of course, like had this memoization, which worked. And actually, our stack-based performs a little bit better. But this is really because the Fibonacci sequence is a very simple one. If we test like for more complicated ones, actually, it doesn't do that well. But this is just a little test to see if kind of numbers make sense. And here we have just a bit of test between our two different implementations, and that everything works out. Just one caveat is that although it is quite flexible in the functional forms it accepts, it still needs to, it can't call other functions. So let's say it can't do f of n equals f of n minus 1 plus g of n something. So right now that's a little bit too far. So we're just still focusing on this, on one function that calls itself in multiple ways.
Mm-hmm.
Right. Okay, maybe I can pause 1 second here, because that was like the introduction and the implementation of the two different functions. If you have any questions, or I can go on.
No, it looks pretty good. So I'm just curious about the memoization technique. Was this something you developed, or was this kind of a standard formula or standard approach?
So I would say both. The part about using a stack to keep track of which function needs to be computed is very standard. I would say like in computer science of how to deal with let's say with recursion. But the memoized part about keeping track of which part of the function we evaluated or not, and using an association and an index for that is like something that I implemented, and that was like the most tricky part to kind of make this all make sense. And that's why we have like actually lots of association, lots of indexes in different ways. Because as we said, why we did this is because we wanted to accept flexible, or I want to be flexible in what function forms it accepts.
Yeah. Interesting. Okay, cool. Great, thanks for that.
All right, then now we're gonna like move on a little bit more into the like exploration phase. And as you saw before, we
Hold
like
on.
sure.
This f of n equals this example of unbounded a condition which
Oh, right. Yeah, that's interesting. Yes.
So it's like that's unboundedness in the sense of like the call tree won't ever terminate into a base condition.
Exactly. Well, actually, yes, that's exactly it. I mean, we could put a base condition saying, oh, f of 100 equals 100.
Yeah.
We could be, but that wouldn't really make much sense. And if we don't have a good base condition, or if our base condition is like a lower result, then we wouldn't actually, I mean, the function would crash. It would just go forever. So yes, that's one thing that we actually haven't implemented, is like kind of safeguarding unbounded growth.
Mm-hmm.
I mean, because we assume that we wouldn't like test unbounded growth, but that's definitely something that I have in the future as a like kind of next step if we want to improve this function to just more or less tell the user you can put functions that exhibit unbounded growth behavior. That's yes, that's definitely like kind of a little test that we need to make at the start to make sure that users are putting the right functions.
Right. That makes sense. Yeah, that's interesting, I guess, because it's like the same problem but in reverse. I mean, if you say, okay, I want f of n to be one more than the one above it, the next one, then you'll have to go to some sort of ceiling and say like, okay, well, f equals 100, f 100 equals like whatever you want.
Yeah.
100, and then f of 99 would then be 101, and f of 98 would be 102, and would work your way down in numerical value.
That's something interesting that I
increasing.
actually could test, having like an upper ceiling and see if our implementation actually works.
So in all of these, it's like you use subtraction, I guess, more than adding to the end value.
Yeah.
That way you could just start low and then work your way up through the call graph. Okay.
Yeah. Okay, so now we're going to look at it essentially. So we saw before there was some explanation done with like these like kind of famous sequences like the Fibonacci, the Hofstadter Q sequence, and some others. And they already found some like interesting patterns. And so for me, we had some idea with my mentor Brad to have operations that convert numbers into its integer digits, applies some transformation to it, and then converts it back to the number. And so this is where we've essentially explored like different ways of doing that. And we actually find some pretty cool patterns and some pretty cool graphs out of those. So just to give you an example, we're not going to go like into every single like implementation, but this is like maybe a simple one of how it works. Here we've got n. So n is our input number. We convert it into integer digits with a specified base. If it's a base of 2, it's just like different zeros and ones. And then there is passed by the user, and it's either takes the most or the rest. So we have a number, convert it into integer digits. We take either the most or the rest. So we essentially cut off the end or the start. We convert back those integer digits into a number. So since we've taken off either at the start or at the end, the number will always be smaller. That's the kind of important part of these shifters. Number always needs to get smaller. As we saw before, this is the problem of unbounded growth. And essentially so we've come up with like different ideas, and we've also like kind of partly explored and also programmatically tested like different combinations with different inputs. And in this notebook or this community post, there's just a kind of a selection of the most interesting ones. So for example, here, this is with base 2, either like to convert the integer digit or convert it back. And it takes the rest, exactly. It takes the rest and with base 2. And we go n equals 100. So we calculate all the results for n equals 100, n equals 99, n equals 98, and we see which numbers need to be calculated for which ones. So for example, in this case, if we call n of, so the input n is 100. So to get 100, let's say we had to calculate 50, we had to calculate 40, we had to calculate 30, like f of 50, f of 40. And then later on, we again have to call f of 50. We've already calculated f of 50, so we don't need to calculate again. So this is not just like inside the function, but also in between functions. Like in between functions, we memoized the values. Okay. Then, yes, this is just essentially the results for essentially the x-axis is the n, and then the y-axis is the result for each f of n. Here we get like interesting pattern, which is like an upward trend. But there's definitely something there. Similarly here, yeah, we have like very kind of central points, and these are very probably those base conditions. this is probably 0 here, where like most of the nodes lead to this point. But there are still some communities like on each side. So what you could imagine happening is for very large numbers, at some point they all more or less reduce down to some specific numbers, which are these ones. These, let's say, I'm not sure, like maybe 8 specific numbers here. They all reduce down to those, and then they slowly all reduce down to 0, for example. That's kind of the general idea. Here we've got all kinds of different kind of interesting graphs that we found, but it's with a simple chop shift.
Interesting.
Right. Then another one, which is also a very similar idea, but essentially instead of just taking the most of the rest of the integer digits, we apply cellular automata rule. And I thought this was pretty fun. It doesn't actually create that much like interesting graphs per se, and also it's also looks very random because of course we just took a random cellular automaton rule out of all of them and then created a graph out of it. But I've tried many different ones. Some kind of magically we find one interesting one, and then some others are not that interesting. But I thought this was kind of like an interesting exercise to have a look at. So we need to use base 2 because we need to make sure that the integer digits are 0 and 1s.
Mm-hmm. That's for 2 color cellular automata. What?
Yeah.
So this is interesting. All right, so I'm trying to wrap my head around this. For the numerical like functions up at the top, it was like, you know, a function of some integer, and then you have this recursive relationship, and it's nested, and you have this call graph. And then so for the other ones that you just mentioned, I mean, can you describe them again real fast?
Sure. Yeah.
I mean the previous section.
Oh, the chop shift.
Yeah, the chop shift. So
sure.
Like,
so if we don't look at the code, chop shift specifically just takes a number and gives a smaller number. That's the only thing that it does. So actually,
so it's like 178, and let's say you take the rest of that and you use like base 10, right?
Yeah.
So like 178 goes to 78, and 78 goes to 8, right?
Exactly.
And so then you're looking at, okay, f of n equals f of chop shift n. Okay, the rest, and then a is the base. Okay. Here I guess you're using base 2. So you have this binary number, and you take the rest of it, and then you have another binary. So what happens if it's like 101, and you take the rest of that? Does that return 1 or 01?
The rest should take everything except the first value, I think. And
yeah. So like if you take like 101 is binary for 5, right? And then if you take the rest of, if you chop the first one off of that sequence of 1s and 0s, that's binary for 1. Does the leading 0 of the rest get,
So I think you can't have, if I'm not mistaken, you can't have leading 0s. So I guess it would just go back to 1.
Okay. And then so the chop of 0, 1 is then 1 again. Okay. And then you have,
I guess already if you have 0 and 1 and you convert 0 and 1 back to a number, it would just go to 1 directly, I think. Yeah.
Okay. So yeah, the chop shifts is just another way of reducing the size of the n that you're
exactly
feeding back into f.
Yeah. So for example, I mean, Fibonacci just minus is 1, but essentially doing the same thing. We're just doing a chop shift instead of a -1 of n. Yeah.
Well, and here it's as chop shift of rest of with base A plus chop shift of rest with base B. Then in this case, A and B are the same, right?
They're the same.
So that's just f of n equals 2 times the f of the chop shift.
Yes.
Huh. Right. I guess that's interesting.
We just have those differently because we were just testing like if A's and B's were different, for example.
Yeah. Okay. And then with the cellular automata, what's happening there?
The automata is very similar. Is chop shift takes the most of the rest. The pseudo automata applies a transformation rule.
Okay.
Like a pseudo automata rule.
Okay. So you have this binary number
Mhm.
expressed in binary digits, and then
Yes.
you want to get a new binary sequence,
Yes.
a number that's expressed in binary, but the transformation is you take this binary sequence and you apply some sort of CA to it.
Yes. And then
And you
take
get
the
next
Mhm.
Okay. So
But you have
that could
the
be that could does that guarantee that the number will go down in size? I
No,
guess
it
a
doesn't.
priori doesn't, right? So it could jump around.
Exactly. Yeah.
But the
That's why
amount, I guess,
here.
if the number of digits is bounded, then you're not gonna jump up too much, right? Like you have this cap of
Yeah.
computation.
But either way, we'll to just avoid any problems, we still take the rest of that transformation.
Oh, I see. So it'll reduce the size no matter what.
Yeah, because I mean, if even if like the increase is bounded, or it doesn't increase too much. If it doesn't like consistently go down, then we still run the risk of like it might just run forever. We're not really sure how it works really, or it might just get stuck somewhere. Yeah. Cool. Is that clear? Okay. Okay. Then, yeah, so flip shift is also kind of, let's say, just a variation of these chop shifts. Again, here we're just converting into integer digits, and we're with a base, let's say, larger than 2, and then we're just minusing 1 each digit itself. And then this looks a bit more fancy and a bit more complex, just because in case we get 0, we don't go to -1, we go to 1. Or yeah, that's kind of the what we're trying to avoid. So here, this is the plot of like just the results of the functions to the input n.
Very interesting plot.
Yeah, so it's hard kind of to explain like what's happening, but it's definitely very peculiar how it looks. But yeah, when I looked at the call graphs of those, it wasn't as interesting as the plot from the results plot.
I wonder what more terms would look like. I guess it would just kind of keep doing I wonder if those nested triangles get bigger.
Yeah, I think I tested those actually, and yeah, they actually do get bigger. So when it's like small inputs, they're very small and close to each other, and the larger they are, the larger like the input kind of limit is, it gets bigger and bigger, the triangles. Yeah. All right, then okay, expand shift is not incredibly interesting. Digit shift is I would say a little bit more interesting. We take the digits and we just sum them up. So 178 would be equal to like 16. So here is like first time we have like actually like distinct, like disconnected subgraphs. So the idea here is that based on like where you start, you might actually only stay within your subgraph. So all these numbers are linked to each other in a certain way, but they're never linked to another number. So for example, like, yeah, so that's the general idea.
They're never linked to another number. Yeah, I see they all go down to the space condition, right?
Yeah, very quickly to the base condition. Here we just went to 100. So there's not that many, but there's the same patterns when we go to larger numbers. like there might be more subgraphs, so the subgraphs might be more dense. They're still like kind of, depending on where you start, actually the sequence, since we're just summing up the digits of the number of, let's say, levels that goes down is very limited. So it very quickly goes down to base condition, and they're not actually linked to many other numbers. Yeah, that's why we have all these like separate subgraphs. Yeah, this is what we saw with the input of 500. Yeah. And then it's it's the same thing.
What's the base condition is what?
Here the base condition is anything under 10 equal to n.
Okay.
Because if we have f of 9, then we just like go back into a loop.
Mm-hmm.
Because we're like, you're summing up 9, 9, 9, 9, 9 all the time. So anything, so from 0 to 9, it stays to 9, but then we just terminate it.
Yeah.
We don't want it because there's nothing else to do anyways. All right. Split shift is again a different way of, we split the numbers. So we chop out the first element. 157 goes to 57, 57 to 7, and it's very, very similar to the previous one where the number of levels that goes down is quite limited, because if it's like it has 4 digits, then it will just go down 4 times. Like each input will go down 4 times. But here we tried it with 1,000, and again the base condition needs to be the same, so that we don't kind of get stuck in the loop.
Now it's the reduction is like you have these like little sections. And then wait a minute, so this is, I see. If it's less than 10, it goes to n. And so each one of these is like 1 through 9.
Exactly.
And they're causally isolated segments. And it's going to 1,000, and so it's, I'm guessing, 100 to 199 is one of these like little flowers here. So if you went to like 10,000 or something, it would just recurse another layer.
Exactly.
Okay.
Yeah, exactly. Yeah.
Got it. Interesting. Okay. Now what's this? We have a Ouroboros. Okay.
Yeah, this is also so this we use this other functional form and with the split shift, but yeah, I'm not sure what exactly this represents. Maybe you guys have seen this elsewhere in the literature or
I mean, are there base conditions, or does this actually make a loop?
Yeah, it's hard to say if it really makes it if it really does a loop or not, because maybe the visualization that Mathematica chooses is might be just in a certain way, especially with like n equals 1,000. Actually, that's actually a good question, if it does get into a loop or not.
Like you can compute the call graph of a looped function that kind of like f of n, like you use like mod 10 each time or something like that, and just like go to the previous one, and then that would recur. So like you would have to set a base condition for it not to keep iterating, but the call graph would be kind of be like a loop. I think it would be interesting. Okay. Interesting. Cool. Second.
And then here it was just actually while at the summer school, actually Brad was also playing around with these shifters, and he had this new like kind of new integer sequence or like new dragon fractal.
Yeah, he showed one of those
that he found. I'll just like show 2 seconds how it looks. And this is just using one of those shifters.
So this is making like turtle graphics on the sequence of the number, or
Yeah, so it's applying like some kind of like shifter to to each angle or like to each point.
Mhm.
So, like, at which angle are we from drawing the next line?
Fascinating.
Can you explain the what's profound about the dragon fractal here?
So I'm not as like familiar with exactly the dragon fractal, but the main idea is that he was using the same concept of these shifters to decide like to essentially change the angle and decide where we're going with the next line. And just from these very simple shifters, he was able to create actually this diagram or like this let's say this shape. That's the kind of like general idea of what he found. So out of like this simple transformation, there was some kind of recognizable shape out of it.
Wow,
I'd say.
that's a cool discovery.
Mm-hmm. Yes. So actually, he wrote this blog, this community post during the summer school. So that was really fun to
Very cool.
see him work on. Yeah. And so yeah, we were actually like discussing a lot about like these shifters in general. And that's how he came up with these other shifters on his own. And I kind of took inspiration from it to also test them on my in my functional forms. And there was also some cool graphs that came out of it. So yeah, excuse the names. The names are a bit clumsy per se. So we were kind of running out of names at some point of the different shifters. So yeah, this is the clumsy shift. Well, the cycle shift looks very similar, but now we put the colors in, and that looks cool. And yeah, it's some kind of like still a bit of a branch, very similar to actually the first few ones we saw. And then here again, yeah, split chop shift length is more or less what it says. It's taking the length of a split, split it up and chopped sequence of integer digits. And here again, we've got those communities that reach certain points and at some point the initial conditions. So the initial condition is probably here, this one, 0, because all the different communities lead up to this one.
I see.
Yeah. Yeah. Same thing with here. The base condition is here. So 0 over here.
Mm-hmm. What? So this is like identifying where the base conditions are that you need. If you wanted to compute numerically these things, you would have to specify those at the bottom. Are those specified here?
If you want to specify what, sorry?
If you want to specify the numerical values of these things, you would have to specify the base conditions. And do you specify the base conditions in order to make the call graph?
So yeah, so essentially to terminate the function to make sure like it stops at some point. The base condition tells us when to stop.
Oh, I see. Yeah, the n less than 1 goes to 1.
Yes.
Yeah.
So essentially it goes all the way down to 0.
Mm-hmm.
Or anything, if we reach something below 0, then we go to 1 and then we terminate.
Got it.
Yeah. Again here, yeah, we got another like.
But wait, hold on. I'm sorry. And that's not specifying what f of n less than 1 goes to. That's just like if the value of n goes less than 1, then.
So it's more like if we call f with a value of n that is less than 1, we don't evaluate it. We just return 1 and then we terminate.
Okay.
We stop the recursion. And then this is our value. So now we know this base condition, and then all the other values that we're waiting for a result to come. Now they've got the result and they can be calculated.
Okay.
And yeah, this is also like a cool kind of, because we got like some bigger ones and then some smaller ones coming out of this, say, initial condition. Out of that.
Mm. They're really cool.
All right, so this is like all the different types of shifters, and maybe I can go back a little bit to the code and show you how we actually created those call graphs. because that's also one thing that was let's say a prerequisite for our recursive function, is that it didn't just want to calculate results. It also wanted to tell us how or what the call graph would look like. What value did it actually have to compute?
Mm-hmm.
And we did this with like a reap and sow method.
Okay.
In all the functions, every time we figured out that a specific, let's say f of 10, if we knew that f of 10 needed f of 9 and f of 8, then when we calculated f of 8 and f of 9, and we went back up the tree, then we sowed essentially this information in a specific format that could be used from by another function to create those call graphs.
Yeah.
So here we sow essentially more or less we more or less sow our memo, because in our memo we know which values need to be were computed for which value. And this is where we find this in the function call graph. This is like this important function where it reaps those values, or like it's not even values, it's information actually, in the form already of a graph, so with edges and edge weights, and labels for the nodes as well. And yeah, it does some transformation, and then we call the second one, which is the call graph, where we actually create the graph. This is just more like kind of aesthetics with the color of the edges, the size, and all types.
Mm-hmm.
But the interesting thing here is more the reap and sow method that we use, because as we go along and as we compute the values, we in our memo and in different parts of the code, we remember what was needed to calculate this, so that later on we knew how to construct the graph. Yeah. Yeah. All right, so that's one thing. Then here, these are more like basic arithmetic operations that were tested out like during the exploration. They're usually not often like actually nested, but it was just more a bit of exploration from the start.
Mm-hmm.
This is actually similar like to this kind of ladder-ish, like the Fibonacci actually. It's very similar, except that it's not 1 and 2, but it's like 3 and 5.
Uh-huh. That's interesting.
Like there's like kind of bigger gaps, because it's taking bigger jumps.
Cool. And this is three summands.
Exactly.
Uh-huh.
With kind of relatively random like 8 variable like parameters inputted, but it does create an interesting shape. And again, we see with the green, that means there's been like three calls back to the function.
I wonder what if you plot this in 3 dimensions, if it would have like a volume.
But yeah, it's probably like something like still some kind of cube, I think structure. So yeah, these are also ladder type things. So
These look like
yeah, it's someone
bacteria.
who's about how interesting it was, but this is like 4. Yeah.
So I guess it would have like the base conditions on the left. A couple of them.
Probably, yes.
Uh-huh.
Actually, I would say I think probably to the right. Probably these two are the last 2 base conditions, I would say.
Oh, and then this is at the edge of what's computed so far.
Yes, exactly.
On the left. Yeah. That makes sense.
Mm-hmm.
And it just hasn't been stitched together yet.
Mm-hmm.
As much.
Mm-hmm. So yeah, this is we use some square root. We don't have something super interesting. This is actually quite interesting, and it starts getting a bit. This is actually nested, and we're using we're dividing f of n minus a and f of n minus b, taking the floor of that, and passing this as a transformation for the next f, and is even nested in another f. So it started becoming like a little bit wonky,
yeah,
in all the different ways. But again, this is a bit of an exploration and looking, but we still find like these kind of like cool looking graphs actually, which is like an unfinished like Ferris wheel, if you may. And here again, we have like, it looks a bit like a coral, and it's still not finished here.
Yeah.
So this again might also be kind of how Mathematica chooses to visualize things. That's also one thing to take into account. All right.
Wow.
So this is where that was all the kind of graphs I want to look at, and maybe I can just talk about what the like next steps of this idea or this project could be.
Mm-hmm.
So one is more the actual like there are functions that we implemented. So as you mentioned before, Dugan, one is like this just preventing this unbounded growth. The second is working with like other functions, but then again, for working with other functions, we need to figure out how we actually want to deal with that in the call graph. That's like maybe a little bit more like thinking through how that would work. And then, yeah, so we've optimized the storage when it comes to computing the functions, but this is a little bit like kind of trivial, but because sometimes some parts of the function could be, for example, 1 plus 2. But then this 1 plus 2 calculation might be found in the other parts of like in other functions. Okay, so 1 plus 2, we don't need to memorize 1 plus 2. It's a bit silly. But maybe there's more complex calculations like that, which could be memoized. So for example, if it's so 1 plus f of n minus 1, and we've memorized f of n minus 1,
yeah,
whatever value that is, we haven't memorized 1 plus f of n minus 1. So, I mean, there's maybe an open question of, should we memorize that at all? Does it really make sense?
Oh, I see what you mean.
Or not? But maybe there's like some complex like combinations of f of n's and of what we call these partials that could be memoized or not. That's kind of maybe like an open question to see if it really helps or not. Like the examples I gave probably won't make sense. But when we're looking at these different floors and which are calculating like f of n's in all different ways, it might be. Okay, and then
well, that would, you know, Mathematica in Wolfram language, that would necessitate like adding down values to these functions such as plus, floor, or whatever. That could get messy if you just you can unprotect a plus, but it's not advisable.
Yeah.
You know what I mean?
Yeah.
All right.
So I would say like yeah, that's kind of the function side. And I mean, in general, I think we're aiming to like publish this on the Wolfram function repository with Brad. So I mean, all the work that goes with publishing a function was like a bit more testing, a bit more like I mean, safeguarding what the user can input and all these type of things.
Yeah.
That's more on the actual function. And then regarding the function space, I would say from like my exploration, these very simple functional forms has been kind of looked at, and like I've kind of like I think tried out lots of different forms, and we do some interesting patterns. There's still kind of so what, let's say, result out of those. I guess we do find some interesting patterns, but I mean, kind of what do we do with it? What really can kind of tell us? I think that's kind of an open question of what it can. And so one thing is like, I guess like exploring the function space even more with like really large inputs. But the limit with that is that actually visualizing then the call graphs of those becomes kind of nonsensical. You just see just a big blob at some point. And that's kind of the limit, I would say, of exploring these call graphs, is because we're still visualizing things. And at some point, if we get really large numbers, however the transformation looks or is, it won't look better than small numbers, and it will look even messier. It will make even less sense. So as you saw before, when you have like this kind of like this like let's say flower, if we just have a much bigger input, it will still look like flower, just more dense flower. But then one that has a bit more interesting patterns on a smaller scale, if we add a lot, we have a huge input integer, then maybe there won't be any more pattern, or like we won't be able to see the patterns because it's so dense anymore.
Yeah.
So that would say kind of the limit of these call graphs. And so actually, one other direction that actually Brad is more working on, that he kept me updated, is they're looking at these nestedly recursive functions, and the question they're trying to answer is, are the other results, or is the output of these functions random or not. And
Right.
how they do that is so my understanding, what they do is when you get the result of a certain function, you transform it to, let's say, just base integer digit to base 2, and you do that for lots and lots of inputs, and then you see, are there any missing blocks? Have we missed a specific sequence of integer digits or not? And if we haven't, then we can like kind of, it's not a necessary condition, but it's like a first step to say, oh, the outputs of this specific function might be relatively random. But if there's actually missing blocks, and maybe at specific intervals or at specific places, then it goes more in the direction of no, the outputs aren't actually random.
Mhm.
So yeah, I think that's more or less everything I had to say about my projects. Yeah, I'm happy to, like, if you have any questions or anything, happy to.
No, it's great. It's really interesting stuff.
That final quote there, as Stephen said, there's a possibility of a more general basis for rules to describe nature. Interesting. So it's like a potentially like more compressed representation for observable phenomena. Is that a good rephrasing of that?
Yeah, and it would be like, maybe applied to this project would be a very simple like transformation of specific numbers. When we visualize those, and we actually get a pattern that we actually see in nature. For example, this ammonite or this kind of like coral-like structure, or even like a flower. So, I mean, maybe to put it like super simply, maybe the idea is that how a flower grows or how its cells grow might be based on a, maybe not a functional form like this, but some kind of rule that seems very simple, right, from the outside, but it still creates something that has a certain pattern.
Yeah. I mean, I mean, what makes a Fibonacci sequence relevant to natural, like, you know, flower petals and stuff like this, is because like there's a certain population, and then like a lot of them are replicating themselves, and then there's like a gestation period or a certain amount of time before the new ones start. There's a delay between when they are born, when they get, you know, made, and then when they can start reproducing themselves or replicating themselves. So with a, you know, each new item takes 1 unit of time before it matures enough to start replicating. If that amount of time is like different, or there are multiple types of things being replicated, and each type has a different like delay in it, then the growth pattern will have more complexity to it.
So basically, another interesting exploration here could be that the golden ratio, as beautiful it is and as prolific as it is in nature, is just one of many such potentially interesting algorithms. And it was maybe one of the most natural ones to find because of how easy it is to construct. But using the power of computation and, you know, the approaches that we're taking here, there could be many such algorithms. And
Yes.
this is a nice way of finding it.
Yeah, I think that's definitely like kind of the general idea of this. Sure.
Yeah. That's very cool. Okay, thanks. Nick, anything from your side?
Well, your question about that, your comment about that there's potentially many more such relationship to like Fibonacci sequences and all the relevant one, because I've seen some video recently like about what are the generalization of Fibonacci sequences, and I kind of wondered what would be also some kind of general approach making those kind of generalization into and making some graphs of them, because they also generalize different kind of similar to golden ratio numbers, right? And how those are relevant to nested recursive functions. And yeah, so this kind of connection is pretty fascinating to explore, I think.
Yeah. Yeah, very cool. Okay, thanks so much for that, Thomas. I really appreciate your time. We put links to this community post in the description, as well as all the references from the community post is also there.
Okay.
Yeah, I think Nestedly Recursive functions is definitely an ongoing area of interest for the Wolfram Institute, and we're looking to potentially do continued research on this. So if there's anybody in the audience, or if you know of anyone that's interested in potentially being an affiliate researcher of the Institute to look at this specifically, please reach out to on our website or join our Discord. And yeah, that will be great. Thomas, do you mind just stop sharing for a moment, and then we'll just close off the stream. Cool. And then also just a couple of announcements. So we've officially got a NKS book club on the Discord channel. So for those of you that have not yet read A New Kind of Science by Stephen Wolfram, then now's the opportunity to jump on board and discuss that with a group of people who are going through it step by step. It's at the moment it's a chapter a week, but we can adjust to that. Also, there's a lot of the book that has sections of it that doesn't have the click to copy code implemented yet. So we're looking at potentially people that are interested in actually converting those to real code to help go through the book and implement that. So you might even be able to get some code as part of the official NKS website, which will be a nice bragging right. So yeah, join us for the NKS Discord. Our first next session is this Sunday. So yeah, that'll be cool. 12 p.m. Eastern. Yeah, so that's all from our side, Thomas. Thank you so much, and good luck with your adventures in Tsinghua. It sounds like you're gonna have a great time there. And yeah, that's all for the stream. Thanks everyone for joining, and we'll catch you on the next one.
Very much.
Thank you. Bye.
Yeah.
Thank you.
Bye.
Thanks, Thomas.